about to start the next presentation, so if anyone could please take a seat. There we go.
Bringing order to the masses.
Yeah, you got to do it. Somebody's got to do it.
Yep.
Our next presenter is George Whitesides from Harvard University, and he's going to talk to us about new ways of measuring density.
I started my research career as an undergraduate as an electrochemist. I was working for a man named David Geske, and we were doing experiments which would never have passed OSHA standards these days. And I survived by accident, more or less. But one of the things I learned at that time was that I didn't understand anything about electrochemistry. And so when I listened to Dick bring up new ideas in terms of engineering potential barriers based on very small charges, excesses of charges, I'm reminded of how little I understand electrochemistry. And I'm very grateful because those are new phenomena. And I point out to those of you who are students that there is a theory of scientific revolutions that basically says you have a revolution when there's a new analytical technique, and the new analytical technique opens a new window. And that's what Dick has historically done. He's opened windows for all of us. And I'm grateful from what I've learned from him, and I think all of us are grateful for these new approaches. And then, of course, my friend and colleague, Alan Bard, has always impressed me with his ability to show that what I didn't understand, probably because I thought I was deeply stupid, I actually couldn't understand because it was actually too complicated for a human being to understand. So thank you very much. So Tony's talk, just finished on space biology, is fantastically interesting stuff. You probably know my son, who's deeply involved in this subject. And I'm going to go in exactly the opposite direction in one sense, and that is that the underlying motivation for what I want to talk about is an interest we have now in delivering analytical methods, technology in the developing world where one has no money, no electricity, no resources, no almost anything. And it's an area which poses some very interesting problems, but I think also offers opportunities to develop new techniques. And the two I want to show you today, one is based on magnetic levitation, maglev, and the other is based on something called MUPS or AMPS, which is multi-phase aqueous polymer systems. And I'll talk about both of these relatively quickly. So first, just to make sure that the list is up there, and all of these people do other things in their life, so these are part assignments, but I'm deeply grateful to them, and I will acknowledge some of them as I go along. All right, maglev exists. It's well known. Here's an example of a frog floating in the environment provided by paramagnetic air over a 17 or whatever it is, 16 Tesla magnet. So this is not simple. The 16 Tesla magnet is not simple. The frog is confused. That is something which is closer to home, and although we're not going to talk about it, it's actually pretty interesting. It's a piece of graphite floating on top of some neodymium iron boride magnets. So those are 0.5 Tesla or 0.4 Tesla. And I show it because graphite is very unusual in a regard that is going to be important for this seminar, in that it has a very peculiar magnetic susceptibility. And then that is simply a set of things ranging from silicon to gold floating in liquid oxygen in a superconducting field. And I'm going to come back to that because it turns out that you can do all of that without the superconducting field in the neodymium iron boride system if you know how to do it, taking advantage of what Rico was talking about, which is low gravity, effectively low gravity. All right, now, how does one measure densities? There are a million ways of measuring densities, and again, one of my scarifying experiences as an undergraduate was trying to measure a density with a pycnometer, in which I knew exactly what the density was and I knew exactly how to do it, and I could never get the right answer. I just couldn't make it work. But of these methods, if you think about them, those of you who do it, they work really, really well for liquids. But if you want to measure the density of something like peanut butter, it's not so straightforward how you measure peanut butter's density, particularly chunky, particularly if you're working with small quantities of stuff. So we set out with this background, and this is useful and important. What you see on this side of this plot is magnetic susceptibility, and this is just to blow up the scale. All these things that are in here, there's 0 somewhere around there, these are all organics. And as a first approximation, all organics have the same magnetic susceptibility. There are a couple of exceptions. Over here is graphite, and for reasons that I still don't fully understand, bismuth is very unusually diamagnetic, but everything else is pretty much the same. And then over here on a scale that's down here, it's about 10 to the third larger, you go up to various and sundry things. These are paramagnetics. So basically, paramagnetics interact much more strongly with magnetic fields than diamagnetics. Paramagnetics are attracted to magnetic fields, and diamagnetics are repelled, but the repulsion is universal and weak. It's actually in everything, and paramagnetism is much stronger. So how do we use this, and what is the basis of the method? And the whole talk is basically summarized here. Imagine that I have a bead or something of that sort, and the bead is suspended. It's a diamagnetic bead. It's heavier than the medium, the liquid medium, and the liquid medium is, for the sake of argument, manganese chloride solution, aqueous manganese chloride solution. So what will happen in the absence of a magnetic field is the bead will sink down to minimize its gravitational free energy. On the other hand, as it sinks down, it displaces a volume of paramagnetic solution. And if there's a magnetic field gradient here, as it sinks down, it displaces the paramagnetic fluid from a region of higher magnetic field to a region of lower magnetic field, and that's energetically unfavorable. And so what happens in a maglev experiment is that you balance a gravitational force going downwards with a magnetic force pushing upwards. And the two of those are expressible in terms of an equation of this sort, in which the relevant terms are basically this B del B expression, which says that the force of the magnetic force depends upon the square of the magnetic field strength. I mean, that's the basic take-home message. And then there's this difference in magnetic susceptibility, and that's pretty much constant for a given medium. And then there's the difference in density, which is what we're going to be interested in measuring. So that's the basic method. Now, if you look at this, you do a simulation, you look at the magnetic field strength in this particular configuration, and I point out that what we use is north to north, that is the anti-Helmholtz kind of configuration. What you end up is a region here where the magnetic field strength is effectively 0, and then it increases as you go toward both of the faces of the magnet. And you notice it's a kind of bottle. A diamagnetic material will tend to be repelled into this region, and in the geometry that I have shown, the gradient along this axis is a little bit weaker than the gradient along this axis, and that's going to be important in the story in a moment. So if you use the geometry that we have, you can engineer this in such a fashion that it's a linear magnetic field gradient, and that makes it easy to do some kinds of measurements. Example, here are some different kinds of polymers. Nature isn't terribly important. You dump them into a solution, which in this case is gadolinium salt, and they all sink down to the bottom. You put this in this magnetic field arrangement, and they suspend themselves by density, and there's a correlation between the height and the density. It's that straightforward. And so I say it's anti-Rocco in the sense that the magnets cost about $3. The medium costs about 10 cents. There's no power, there's no nothing else. That's all there is to it. My kind of thing. I can actually understand it. What can you do with this? This just gives you an idea of sensitivity. To take an example here, this is a bead, an aminated bead that's been acylated with in this particular case, it looks like carbon-12 methylamine, just ordinary methylamine, which is up here. If you put in 1 carbon-13, you get a very substantial difference and can easily measure that. You put in a CD3 or something of that sort, it gets to be a very large difference. So that you can easily measure in these kinds of things, the difference in weight of a single isotopic substitution. And here is just an example in a real case. Here are these two things differing by 1, and you get big changes in density for that kind of experiment. So it can be, I'm going to show you, it can actually be quite a sensitive methodology. Another characteristic of the method, which is convenient for many circumstances, is that the density that you measure is independent of the volume, so long as the gradient is linear. So here's a 2 millimeter bead, and there's the same material, and it's a 0.2 millimeter bead, and it's the same. Is there any limitation? And the limitation comes when you get down to sizes that are in the order of some microns, where Brownian motion is simply, the interactions of Brownian motion are simply larger than the magnetic and the gravitational buoyant forces, and you start getting a smearing out of things. If you do an analysis of these kinds of distributions, you probably end up with the same number, as I'll show you in a moment, but it isn't something we've spent much time doing. Now, there are two kinds of measurements, and this little slide summarizes very briefly the difference between chemists and physicists, in the sense that as a chemist, I long ago learned in studying electrochemistry and other areas that I didn't understand anything, and so it was safer always to work with internal standards. So here I have an unknown, I have two internal standards, and all I have to do to get the measurement of this is to know what that is and what that is. Physicists don't like doing things that way because they like to think deep, pure thoughts, and so they like to leave out the internal standards and understand the system. It turns out that actually you can't get the real answer in either case because your internal standards depend upon how well you know your internal standards do, and that's not trivial to do. And there's an awful lot of stuff in this kind of experiment which are little things but which really do make a difference. In any event, if you look at measurements, and I'm not going to go through this, if you look at the relevant numbers here, what you see is that the kinds of densities that you can measure if you do this correctly using this technique is in the order of differences in density of 0.0002. And you can do that with chunky peanut butter. And that's actually pretty interesting because it's a new capability if you're in the chunky peanut butter business or in other corresponding activities. What else can we levitate? Now this is my slide on applications. And water, oil, milk, rice, peanut butter, chunky, string cheese, honey, ketchup, crystals of various sorts, aspirin. Is anyone interested in any of that? Well, I mean, that's actually sort of interesting. We had at one point an active collaboration going with one of the crime labs in the South Coast in Los Angeles, looking at fragments of gunpowder left over from something. And there's an entire world that's interested in what's called glitter. And glitter is the little speckly things that those of you who use eyeshadow put over your eyes, and glitter turns out to be an important part of every crime scene. So how do you measure 100-micron glitter particles? And we can measure 100-micron glitter particles. So much for deep fundamental science. Here's another example of something, just to give you a notion. What this is something which actually is a useful new technology. That is that if you're interested in crystal polymorphs, and often when you're making polymorphs, you get very small amounts of things and they're sort of mixed up. How do you do separations of polymorphs? And what you do is you take the polymorphs, you put them in here. They usually have slightly different densities, and the densities here are 0.26 and 0.28 or 0.29. That's easy to separate. You suck them out, and you can then use this for controlled seeding and crystallization. Now, there's an interesting thing that you can do. If you remember, I told you that you could, that the magnetic bottle in this was sort of elliptical. You say, well, why don't you turn it on its side and get greater sensitivity? And you can do that. If you take this device, instead of having the magnetic field this way, you do that, what happens? And this is an example. Here are a bunch of beads which, with a vertical arrangement of the magnetic field axis, you get them sort of clumped together. You turn them on their side, and this is the kind of discrimination you see. Here, this is 1.70, this is 1.165 or something like that. Very clear separation at that kind of level. It gets to be hard actually to use this because you need standards or you need exquisite understanding of the details, but there are experiments that you can do here that are empirical, but nonetheless very useful. What, in some circumstances, this is a capsule of something in which there are a bunch of little pillets in there. And if you'd like to know something about the difference, the heterogeneity or homogeneity in this, if you break it open and suspend them, you get a kind of Gaussian-like distribution. But if you take this and turn it on its side, this is up here, that's 1.324, this is 1.332, so that you can get a distribution in densities of, you know, really very, very small numbers. But it's relative to something. That's an internal standard. And here is the sort of interesting experiment. So I said to you that what you do in these is you balance the magnetic force, magnetic buoyancy, and the gravitational buoyancy. If I turn the thing on the side and the magnetic force, the vector in summarizing the magnetic force remains in the intermagnet distance, but the gravitational vector goes straight down. And that means that as I turn it, I can, of course, tune the gravitational vector along that axis to go be any value from 1g to 0. And when you get down to a low enough value, what you can do in this same apparatus, which is a piece of, you know, just manganese chloride, I can measure any density, basically, that is accessible. And using this tilted arrangement, here are numbers. The same device will take you anything from the density of an air bubble, which is 0.00, to the density of osmium, which is 22.6. The number we get is 22.5. The accuracy obviously scales with the size, but you can measure using a single couple of dollar device any density that's in the range of known materials, which I think is pretty neat. Now, topic A. Topic B. This is another really just turning out to be very useful. I'm going to go through this in a slightly different way because the objective here is not to make any new analytical technique, but to solve a problem. And the problem that we're going to solve is detection of sickle cell disease. So how do we do that? And the technique is based on systems called either MUPS or AMPS, and I put both names up because depending upon which of my colleagues and coworkers you talk to, they'll tell you about one or the other, but they're the same thing. So multi-phase polymer systems are aqueous multi-phase polymer systems, which were originally developed by a gentleman named Albertson in great detail in the 60s. He was a very early bioengineer, and he developed these systems to do some problems in bioengineering protein separations. The idea is the following, that if you take a system that is, I'm going to just make it up, it doesn't make any difference. It's something like dextran, 5% in water, and then polyethylene glycol, 5 or 10% in water. These are systems that are essentially pure aqueous polymer systems, perfectly biocompatible. But they have the very interesting characteristic that they're insoluble in one another. So you have these two phases, both of which is 90% water, and they're insoluble. And what then happens is that you put them together, and what he was interested in was partitioning. So there you will easily get systems that have slightly different hydrophobicity or hydrophilicity. And he was interested in partitioning proteins and sometimes organelles between these two phases. And it's a useful method. It's been used to some extent for initial stages of large-scale protein purification, but it's not a very widely used method. But what we have noted is something which is, in a sense, obvious, and that is that if these two phases separate as they do, what that means is there's a difference in density between them. So what you have now are aqueous polymer systems, almost entirely water, which have the characteristic that they have a thermodynamically stable density step. And that thermodynamically stable density step can be as small as 0.0002. Actually, one more zero if you want to really make it difficult. So that you can make phases with interfaces with incredibly small, or at least incredibly small to me, density steps that are perfectly stable, unlike what you get out of density gradient centrifugation. So although you can't see it very well here, this is a system in which there's a phase here with the density of 1.08 and a phase here 1.080. This is 1.078. And here's a bead floating at the top interface. Here's a bead floating suspended just at this interface, and then this is a heavier bead and sits at the bottom. So the key issue here is that they have they're thermodynamically stable phases. So once you spin them out and they separate, they don't diffuse apart. And they have a very low interfacial free energy, so they don't tear things like cells apart as the cells move through. And they're largely biocompatible, so you can have worms and things like that live very happily in these media. Okay, so here are examples of, this is a 5-phase or 6-phase system with various beads sitting at interfaces. And you can look for yourself at the range. This is 1.04 at the top and 1.15 at the bottom, and these are what they are. And this just shows you the distribution of phases. And these boundaries between phases are, in fact, atomically sharp. So they're whatever capillary roughness is for 2 phases with a very low interfacial free energy. There'll be some roughness at those interfaces, but no solubility. It'll just be slightly rough. So they're very interesting systems from that point of view. Can you design them? We set out with some patient undergraduates to sort of investigate how many of these you could find. And there are lots and lots of aqueous polymer systems that form 2 phases. You start putting those together, and you get to systems that are 3 phases, and so on. We have some now that are 5, 6-phase systems, and I think one could go beyond that if you wanted to. But since you know each of the individual phases, you can begin to make first approximations of systems that are designer differences. And then you can tune the phases in pretty straightforward ways. One way that works well with biology is just to use D2O, H2O mixtures, and that gives you a background density difference that is tunable, and in that case the density differences are linear. Or you can put in barium chloride or something like that, so you could change the density that way. There are lots of ways of doing it. At the end, if you want very small density differences, you do have to do, in our experience, some empirical tinkering, but you can make a pretty good shot at getting to something that's an attractive system without making that much effort. All right, and this is just before I go into the actual application, one demonstration of yet another kind of use. I've said that what we are using these for is phases that are different in density, but I note that the phases are also different in a lot of other things. They're different in index of refraction. In this particular case, they're different in viscosity, so that you can make a series of layered phases. And what we've done here is simply to take layered phases. We take a mixture of the kind of junk that you get when you're making gold quantum dots, put it on the top and centrifuge it, and based on the hydrodynamic drag as you centrifuge, you can get separations into things that look like that, and like that, and like that, you know, the junk grade stuff. So it's actually a pretty useful, specialized method of doing other kinds of separations. So, the strengths to carry away from this: thermodynamically stable phases, if you want to, very small differences in density, biocompatibility, and I'm going to talk about cells in just a moment. This can be scaled to large quantities. There's no reason why you can't use, big bucket centrifuges. The only reason we use a centrifuge is that these phases, because they have the same density, if you start with an emulsion, it can take a while for them to separate. You put them in a low-speed centrifuge, and they separate and spin right down. And they're very easy to use and very stable and non-toxic and so on. So now, what can you do with them? And this is going to be the basis of what I'm going to show you. If I have here 2 phases, and here's the step in density, so the low density phase and the high density phase, and I put something, I suspend in this a few polystyrene spheres, 10 micron polystyrene spheres in this case, with the density in between them. If they're suspended, you can't see that they're there. I mean, they're just little speckles of stuff. But you do this separation, what happens is all these spheres come and they sit in a 2-dimensional interface. So you get the maximum concentration that you can get that way. And it gets to be incredibly easy to see very small quantities of suspended stuff. How do you use that? Well, here's an example with a different kind of object, which is a cell. So this is blood. You put the blood in the top, and I'll show you how to do this, and with the appropriate phases here, what you end up with in the upper set, these are mononuclear cells, these are polynuclears, and these are normal erythrocytes. And the key thing is that if you see this very thin layer there, that's the polynuclear systems separated into a very small layer. So it's easy to see them and easy to separate them. Now, we're using these systems for a number of cell-based separations. It's a very, very interesting technique because you can do more things with it than you would necessarily expect. I want to show you one particular application, which is the detection of sickle cell disease. And this red coloration that you see here is the distribution of sickle cell. It occurs in this region because it and thalassemia and a number of these other blood disorders all have the characteristic that they're protective against malaria. And it is at least believed that that's the region for this distribution. But it's a big deal because in Africa, the number of children, basically children born with sickle cell disease in Africa die. Even though you can deal with it relatively easily in a medical sense, there's no intervention that allows you to there's no diagnosis that allows you in a practical sense to see what's going on. So we wanted something that would be in principle useful in field testing. So now, what is the problem we were dealing with? Here's a normal erythrocyte, and this is a sickled erythrocyte. The characteristic size is this. Here is the distribution of density in normal erythrocytes, and here is with erythrocytes without sickle cell disease. And here is the distribution of densities in an individual with sickle cell disease. There's a broader range of things, and the cells up here are the ones that are characteristic of sickle cells. Now, this number is 1.10, and the number that's somewhere in here is 1.09. So it's a 1% difference in density the one is talking about here. So without going through a lot of the details, what we've done is to put together a system with either 2 or 3 phases, depending upon what we're interested in which we separate out the different kinds of cells, with the key element being the fact that the sickled cells, because they are the most dense, go to the bottom of the system and on centrifugation. So what you see here, and the colors are a little bit less obvious than perhaps they should be, but these are packed erythrocytes, so that what one is getting there is basically a hemocrit for nothing, since you put in the drop of blood, and this tells you how much of normal or normal densities you see. But if you look down here in each of these systems, you don't see a red color here, you do see a red color here, you see a red color here, you don't see a red color here. That red color is sickle cells. So this gives you an indication of sickle cell disease, and although I won't go through the details, there are a series of hemoglobinopathies that all sort of cluster. They're different variants in normal hemoglobin. There's fetal hemoglobin, there's hemoglobin A, B, and C, there's sickle cell hemoglobin, and no test right now can discriminate among all of these, but this does a pretty good job in telling the difference between sickle cell disease, which is homozygotic, in which both alleles have the same thing, you have the disease, and sickle cell trait, where one does, but you're able to get along because basically half the hemoglobin is okay. And incidentally, it's interesting, one of the treatments of sickle cell disease is treatment with hydroxyurea, which takes, it seems peculiar, but what it does is to turn on the re-expression of fetal hemoglobin, which is a different thing and which provides enough normal normal behavior to get around the problem. It's one of the few cases where I know that a simple chemical turns on a silence gene. All right, so how do we actually use this? It's a very clever system put together by A.J. Kumar. What you have is a tube, and the tube has a little polyethylene sleeve, and there's a hole in it. So you take a finger prick, you bring the tube up to this, capillarity pulls the blood up to there,
so that you get automatic sampling to that level. Then this has the level of polymers solutions in it. You slide this up so that you don't get blood splashing around, and then you centrifuge it. And when you centrifuge, what happens is you get blood segregating in the fashions that are indicated. Now, what AJ did was to take this system, and he put together for himself a backpack, which has a battery to run his little centrifuge, and then some various things that are down here. And in the world of the modern university, you go through all the kinds of stuff that's required for for regulatory clearance. The Hospital Review Board has to go through all this kind of thing, and there's batches of stuff with FDA wording and batch numbers. Anyway, goes through all that, and these are what are called the receiver operating characteristics. And the plot here is a plot of the sensitivity of the test to what you're looking for, and down here is the specificity in such a fashion. This is highly specific and this is highly sensitive, and you want your measurements to be up here. And this is what you get in Cambridge, Massachusetts. Now what happens when you get in Zambia, where various interesting things happen. That's where Zambia was. One of the interesting things that happened was that he shipped over a batch of these tubes. It went into the airport, and the airport then had a fire. And so everything was impounded while the temperature went to 130 degrees for 5 or 6 days, and that batch didn't work so well, but that was anyhow it worked. So AJ, I go through this because AJ illustrates what I think is going to be more and more a job of those of us who work in universities to try to make things real. Here are the bush taxis that he took to went off to, distant sites in various places. And the real world receiver operating characteristics look like this rather than looking like that. What we have to do with this now is to tinker with that to bring it up there, and that involves all the kinds of things that one understands how to do, which is stabilization against temperature, stabilization against oxygen degradation, adequate quality control at the beginning, and all the rest of that. But we're very optimistic that this will work, and it has the potential to be very widely used because the economics is right for this. So those are my two stories, and I offer these to Dick, and I guess all three of my predecessors. Alan, I'm sure, thinks of this as being pure engineering and that it doesn't leave you confused at all because it's actually designed to be cheap and work, but you don't have to know how it actually works if you don't want to. And with Rico, I haven't spent $10,000 a pound to move anything anywhere, and I barely feel like a man under those circumstances. And for Dick, it's pretty primitive analytical chemistry, but I hope that in some sense we follow your lead in many things in opening a window which might be useful for something. So congratulations to you, and I thank those of you who have also contributed to the symposium.
Do we have any questions?
Yeah, you showed for the spheres that it was independent of size.
Yeah.
The one particle there that was actually anisotropic, the Rice particle, it appeared to line up vertically.
Yeah.
The question is, do they always line up vertically? And if they don't, do you get a different measurement if they're oriented differently with respect to your field direction?
This question leads in a very interesting sense into a different area in this. What you're seeing in that circumstance is in fact something that if you make little spheres and whatever, or little rods, you can show that there is an aspect ratio where they will flop on their side, and that's just a minimization problem. But you can do something that's really very interesting and important, which is that you take something that is an irregular shape but heterogeneous in its density, either because you make it that way or for something else, and you get three-dimensional orientation this way. And the application, I think, for this is going to be in dealing with something called the poising problem. And the poising problem is the following thing. If you're doing a robotic assembly of something, you got a bunch of screws or whatever it might be, you want the robot to reach into this and grab the screw the right way and then put it in a screw hole or whatever it might be. And it's not so clear how you do that. And you can either make a robot with an expensive, exotic vision system, or you can make the system present itself in 3 dimensions in such a fashion the robot knows where to go. And that what you're suggesting, if you do it the right way, you can go into that entire issue of three-dimensional orientation, and it'll work well. So thank you. Christian?
This was fantastic. But I have a concern about the temperature.
Yep.
Since you are looking so teeny difference in the densities, the temperature control has to be extremely good.
Yeah, it depends upon what you want in the way of accuracy. And so, for example, the perfect example was that thing where we broke open the pill. What you want there is a distribution in densities. If you actually want an accurate number for density, temperature is going to have to be controlled. You're going to have to know the density standards that you work with, and we have no idea how you really get density standards that at a given temperature and atmospheric pressure have the characteristic that I know exactly where they are. You have to worry about making up the density of the solution. Can I really make up a manganese chloride solution that's accurate in all of its characteristics to 5 or 6 decimal places? So the issue of sensitivity and accuracy here, this is a very sensitive method. The accuracy is going to depend on how it's operated, and that's more complicated. There isn't a lot in practice. You know, for most of the things that you're interested in, it is true that there will be a difference in coefficient of expansion of an aqueous manganese chloride solution in a polyethylene bead or whatever you're using as standard. But the difference is not going to be fantastic over that range. Over some much larger range, it could well be important if you're interested in high sensitivity. At some level, yes, because the characteristic of the system is that if you say that the paramagnetic defects have a magnetic susceptibility that's, I'm going to make this up, but let's say it's 10 to the third greater than diamagnetism, and we can do something that's one part in 10 to the fourth or 10 to the fifth, then you can work backwards and do the calculation pretty rapidly. It's obviously not going to be defects at the level of a part per billion, but at the level of a part per 1,000 to a million, I don't see any reason why it shouldn't work. And you can obviously make up test systems in which you put in small amounts of paramagnetic stuff, and it's easy to figure out what the sensitivities are in a particular system. And yes, you can see very low concentrations of paramagnetic ions dissolved in a diamagnetic medium. Alan.
So, as far as I understand it, if you shine light into one of these things that absorbs the light, you will in fact change their magnetic properties, right?
Mm-hmm.
Can you measure that? Can you see?
We haven't tried to do that. It's a good experiment, and it's one of a number of things that we've chatted about, but we've never tried to generate a lot of triplet states in something or looked at something as it was phosphorescing and hoped to catch the triplet in real time. But I don't see any reason why it shouldn't work. Because this technique as a technique is astonishingly sensitive. Yeah. And but particularly for the kind of thing where you're saying where you don't actually care what it is, you just care whether it changes a little bit when you shine light on it. The trick, I think, there would be a little bit that as you shine light on it, you're putting energy and there'll be a local change in temperature and density, and you're going to have to figure that out. Ma'am. If you have the particles piled up so that they're actually in contact with one another in the magnetic bottle, and the set of forces that are interacting on a single particle will be magnetic, gravitational, and then these collective van der Waals interactions, yes, I think you can get a number of metastable states under those conditions. I think if you really want to get high sensitivity, ideally you'd like to have each particle not talking to any other particle. Sir, last question. Yep. Well, I mean, the question is, how do you deal with little air bubbles and things that could change the density? And I think in some cases we do straightforward things like
effectively freeze thawing, evacuating and letting the bubbles pop off. You do this a couple of times. Ultrasonication will sometimes do something. But I think there certainly are cases in which trapped air bubbles or defects or things of that kind will influence the density. And I don't think this solves every problem, but that's just one of the ones that you have to worry about if it looks like it's going to be an issue in the system you're concerned with. So it's a legitimate question, and there's no universal answer. Thank you all.